Hello. My name is Annie Cook, and I work at a startup called Nylas, where we use almost exclusively Python to help other developers leverage their communications data with our email, calendar, and contact APIs. Almost 3 years ago, we made a big decision to start using Mypy. This decision was not made lightly, and it was not an easy transition. It seemed like added work, and many engineers were pretty against that in the beginning. But over time, Mypy proved to be beneficial in terms of code quality, code stability, and engineering speed. So for this talk, I will share how we were able to convince our engineering org to use and eventually to like Mypy. We'll start with talking about what is Mypy, and then I'll go through some basic examples of using Mypy and the benefits of it, and I'll finish with how we added it to our dev process. So to start, what is Mypy? The first place I went to answer this question is the Mypy docs. Mypy is an optional static type checker for Python. Initially, when I read this, I found it more jargony than helpful. So I'm going to break this down for people who, like me, might not initially grasp what this means. The core is that Mypy is a static type checker. And in order to be a static type checker, you need types to check. But Python is a dynamically typed language, which traditionally means that there are no types specified in your code. Instead, the Python interpreter checks the types of the variables as it's running the code. The argument a to this function foo doesn't have a specified type. On subsequent calls to foo, we can pass it variables with different types. The first time we call foo, we pass it 3, which has type int. The second time we call it, we pass it a string, hi. And the value of a has type string. The important thing here is that it's OK in Python to pass variables of different types to this function. This is different from statically typed languages like Java and C, where the types of the variables are specified in the code. And these types are checked before the program is run, usually when the program is being compiled. On the right is how you would write foo to accept and return a string on the top, and on the bottom to accept and return an integer. Having to specify these types in your code seems a little less flexible and maybe less ideal. But there are a lot of benefits to static type checking. Types are a form of code documentation, and they decrease the need for other forms of documentation like docstrings. Because they are self-documenting, it can make the code much easier to understand. Within the function definition, you can see the types of the arguments and the return type. You don't have to comb through the whole function in order to understand that. Also, having to write types forces engineers to have to think about the shape of the data they're working with, which can lead to cleaner code and more well-defined interfaces. All of this helps engineers reason about code. Also, static types give more context to the tools that you use, which enables linters and IDEs to do things like type-aware suggestions and code completion. And finally, static types helps you catch type errors, which are very common, and reduces the range of scenarios that you need to test for. And static types can help you a lot when you're doing code refactors, because it's easy to tell that after the refactor if you've broken any of these types. So Python engineers wanted some of these benefits. Even though Python's a dynamically typed language and doesn't need these types to run, PEP 484 introduced type hints. You can still use types if you're using an older version of Python. On the left, we have how you would write a type annotation for Python 2, where it's in the comment beneath the function definition, and the tools you use just have to know to look there. On the right is how you would write it in Python 3, where it's supported in the Python language, so the type annotation can go directly in the function definition. These type hints alone don't add new behavior. Instead, they enable other tools to add this new behavior. Let's consider this function greet, which accepts a string parameter called name. Name should be a string because we do string concatenation, which will error if anything other than a string is passed in. But nothing is stopping me in this code from passing an integer to greet. So let's see what happens when we pass this integer 3 to greet. Not surprisingly, we get an error. And if we look at the output on the right, we see that greetings was printed, which means the function greet was run. Line 2 printed greetings, and then we encountered an error on line 3. This is all to show that even though we see that the type of the variable name must be a string, and we see that we're passing it in integer 3, which is nothing is stopping us from running this code, and the Python interpreter will merrily carry on until it runs into this error. And this doesn't seem ideal when all the information is right there. Shouldn't something be able to catch this? And that's where Mypy comes in. Mypy is a type checker, so that if you say that the function greet accepts a parameter that is a string, Mypy will search through your code base, find everywhere where you use greet, and ensure that you're always passing it a string. And if it finds any violations, it will print those as errors. So now that we know a little bit about what Mypy is, how can you use it? First, you have to add type hints to any of the functions that you want to run Mypy on. And then you can run Mypy on a file or a directory. So type annotations for Python 3 go in the function definition. You specify the types of the arguments, and then you specify the return type of the function. The types you can use in your type annotations include the built-in types in Python, like str, int, bool, float, and then also you can import more complex types from the typing module, like dict, list, set, tuple, iterable, which are Python data structures. Plus union, which can be multiple types. It means this variable, if it's union str, int, is either a string or an integer. Any is compatible with every type, and every type is compatible with it. So any is useful if you want to allow a variable to just be anything and you don't want to have to define a specific type for it. Optional says that it can be the specified type or none. So now to run Mypy, first you have to pip install it, and then once it's pip installed, you can just call Mypy on a file you want to check or the directory you want to check. So back to our function greet. Here we're calling it again with that integer 3, and then we're also calling it with a string pygotham and setting the return value equal to a variable greeting. Let's run Mypy and see what happens. Incompatible type int, expected string. So here, Mypy is catching the error that we were hoping would have got caught in the last time we were looking at this function. It's saying, you're passing me an int, but I wanted a string. The next error it prints is error, greet. Greet does not return a value. So it's saying, what are you doing? You're setting the return type of greet to a variable greeting, but greet doesn't return anything. If you look at the function definition, it says it returns nothing. It's also important to note that these errors are coming from where we're calling greet. So Mypy, before running any code, Mypy comes in and it just looks at what you've typed and it can tell you if there are any errors in that. Mypy also does some helpful type inference for objects. It can infer the types of an object's attributes based on the types of the arguments to the constructor. So for example, the argument topping is a string. And Mypy can infer that the attribute topping will also be a string. Let's look at this function shopping list, which takes in one argument, pizzas. And that's a list of these pizza objects defined above. Looking at the code, it does set comprehension and returns a set of pizza.topping. The return type of shopping list says that it is a set of integers. But we know, and Mypy knows, that this should be a set of strings, because pizza.topping is a string. This error says set comprehension has incompatible type, set str, expected set int. So it's saying my type is saying that it's going to be a set of integers, but what I received was a set of strings. So we need to change that type. Mypy can also infer what objects an attribute has. And so if instead our shopping list returned a set of pizza.toppings, plural, Mypy would know that this is incorrect. It says, error, pizza has no attribute toppings. Maybe you mean pizza topping. So it's even giving us a suggestion here. Adding these static types and using Mypy is more work up front. But next, I'm going to talk about why it's worth it. First, you get all of the benefits that I mentioned before of static types. And I want to focus on this last point, which carries a lot of weight in my opinion. Mypy catches a lot of errors, and it does so early on in the software development lifecycle. Why is this such a big deal? Well, engineers are humans, and humans make mistakes. And mistakes are costly. You would hope that you catch a bug when you're in development and it's quickest to fix. But that can be hard to do. So next, you hope that you've written a test that will catch this bug. But it's tough to write tests that capture every scenario, and it's likely that your tests will miss some edge cases. And if the bug is in one of these edge cases, then it can make it out onto QA and staging, where maybe it affects the work that other developers are doing. Perhaps multiple people in parallel are now spending time trying to debug this issue, and that can be costly. But catching this bug in QA or staging is still much cheaper than if it makes it out into prod, where in a positive scenario, even a harmless bug will still take time and effort to detect, fix, and redeploy. In a negative scenario, the bug could affect customers, it could corrupt the data store, it could damage your brand, and even still take lots of time and effort to detect, fix, and redeploy. The further your bug makes it in the software development lifecycle, the more costly it is. Mypy tightens the bug detection by catching bugs early before code is ever run, and quickly, without needing to write or run tests. Critics of static type checking will say that it is more work, and it is more work upfront. But there's an underlying theme to all of these benefits that I've mentioned, which is that it helps engineers move faster and ultimately saves time. If you're used to a static type system like C or Java, at this point, you're probably not impressed, because I haven't added anything to the age-old argument of static versus dynamic types. Where Mypy really shines is that it can be added gradually. You can call Mypy on files that have a mixture of functions with type annotations as well as functions without type annotations. And anything that doesn't have a type annotation will have the assumed type of any. And this allows you to incrementally add Mypy to your projects. In the Mypy docs, there's this quote: "No need to give up dynamic typing. Use static typing when it makes sense." The fact that we can write quick scripts without types and have core production code with types makes it versatile and incredibly powerful. So now, how did we go about bringing Mypy to Nylas? It was early 2017. We were using Python 2.7. We had over 130,000 lines of Python code, over 5,000 function definitions. We were 12 engineers and growing, and we had 0% type annotation coverage. Why bother? Well, we wanted all of the benefits of static type checking that I mentioned before, and we also wanted Mypy to help us transition to Python 3. When I say we, I mean one engineer who spearheaded our Mypy efforts. They began adding and checking type annotations as they worked, and they started to see some benefits for themselves. Their metric of success for this was the percent of functions with Mypy verified type annotations, also known as type coverage. So this one engineer adding types to functions and checking them with Mypy, we'll call this phase 0. And in phase 0, our progress, our type coverage, was trending upward because we went from having no types to all of a sudden having some types. But since they were just a single engineer out of 12, there was only so much that they could do. And our progress started to decrease. Which brings us to phase 1. Type annotations were decreasing because the 11 other engineers were not updating their type annotations and not running Mypy, which means they were breaking some of the existing type annotations as they worked. And so in response, we added a step to our dev process, which automatically ran Mypy on all files on a commit and blocked submitting it for review if there were any errors. We use Fabricator for our development platform and Arcanist for interacting with it on the command line, so we created another Mypy linter, which just automatically runs anytime a developer submits their code for review. And this is open source in our Mypy tools directory. This slowed things, but progress was still decreasing. Let's consider this code scenario. We have a function greet, which is defined in salutations.py. It's also used in salutations.py, but then it's also used in another file, welcome.py. Greet takes in one argument, name, which is a string. Then we refactor greet to take in another argument, excited, a Boolean, and we refactor where it's used in salutations.py. But we forget to refactor where it's used in welcome.py. Phase 1 only checks the files that have been modified in a commit, so it wouldn't catch the fact that greet in welcome.py is not passing the correct arguments. How can we fix this problem? Engineers are breaking type annotations in other files. Our response was to add a step in our dev process where we run Mypy on the entire code base. If Mypy fails anywhere, then we block landing that code. We use Jenkins for our CI process, so we just added another build step that runs in parallel with the other builds, and it basically just calls Mypy on our entire code base. And if there are any errors, it blocks that commit from being landed to master. With phase 1, our Mypy linter, and phase 2, our Mypy build, existing types were not going to be broken going forward. But even still, our metric of success was decreasing. Less rapidly, but decreasing nonetheless. Although one engineer was adding type annotations as they worked, the rest of the engineering team was adding functions without type annotations, which means that there were more functions being added without type annotations than with type annotations. And thus, our metric of success was still decreasing. Which brings us to phase 3. In order to make forward progress, we needed the entire engineering team to contribute and add type annotations. We wanted to do it incrementally, in a way that wasn't such an upfront burden. And so we added another step in our dev process that forces engineers to have to add type annotations to untyped functions that they have added or modified in their commit. To do this, we built a tool that, for any new or modified line, looks at the function definition that that line belongs to. And if that function definition is missing a type annotation, then it prints an error, kind of like this. And we did it this way because we figured engineers had some ownership over those functions since they were most recently adding or modifying them. So this would be a good time to ask them to add types. And this step is run before we actually run our Mypy linter, because we want to make sure those types are in place before we actually run Mypy on them. And this tool is also in our open source Mypy tools repository. So with these 3 steps in place, our Mypy coverage could not regress. It could only increase. So then we just had to wait for these types to be incrementally added. And engineers were not initially happy about these extra steps, especially this last step, which forced engineers to have to spend time adding types. I myself was one of those unhappy engineers. I joined Nylas early on in the Mypy transition, and I was eager to submit my code. I just wanted to move quickly, submit the code. Why did I have to spend time tweaking type annotations just to appease Mypy? But over time, I started to see some reason to the errors that Mypy was pointing out, and eventually Mypy caught me from committing some pretty devastating bugs that would have had terrible repercussions had they made it out onto prod, which converted me into being a Mypy advocate for our team. Here are some tips to turn your engineers from skeptics to Mypy proponents. First, create guides. For people new to Mypy, just basic guides on type annotation syntax and common data types that are found throughout your code base can be really helpful in ascending the steep Mypy learning curve. Also, explain the benefits. A lot of the benefits for using Mypy are kind of long-term benefits because Mypy gets more powerful the more type coverage you have. The more types are in your code base, the more context that tool has, and so it can give you better errors because it knows a lot more about what's flowing through your system. But this is hard to grasp in the very beginning, so just explaining that benefit to other engineers who might not understand it is a good way to get them to buy into the process. Help each other might seem silly, but a big thing that helped our company with this transition was the engineer who was spearheading the Mypy efforts was always willing to jump in and pair on any complex type annotations or any Mypy errors that didn't make sense, just to ease the process. And finally, remember that things will get easier. As more types are added to your code base, it also gets easier to add new types because you have more information about what's flowing into your functions and out of your functions. And you just get more familiar with the Mypy errors and you're quicker to fix them. With these steps in place, our coverage was finally increasing. And these are still the current steps that we have in place almost 3 years later. So now, it's late 2019, we're amidst the transition to Python 3, and Mypy is helping us with that. We have over 280,000 lines of Python code, over 11,000 function definitions, 30 engineers and growing, and 80% type coverage. A lot of the remaining 20% is code that we no longer use anymore, like outdated scripts or old database migrations. So of the code that's currently running, we're closer to 90 or 95% type coverage. And the crowning moment of this for us was when the longest standing Mypy skeptic said that Mypy was helpful and they were actually happy that we used it. So some things that we learned along the way that made this transition successful is first, build Mypy into existing processes. The fact that running Mypy wasn't an extra step or wasn't up to each engineer to have to remember to do was a big thing that helped and kind of forced buy-in on our engineering team. Also, don't let your coverage regress. And if you see that your coverage is slipping, that's a sign that you need to add more process. Finally, it takes time. But Mypy gets more powerful as your coverage increases. So don't let the experience in the beginning of adding Mypy to your project be the basis of your decision whether to continue with it or not. And finally, stay strong. People will grumble. Engineers are busy enough, and no engineer wants to do what seems like unnecessary extra work. But Mypy takes time before it proves its true colors and wins people over. So stay strong in the meantime. We did all of this almost 3 years ago, and it's only getting better. Mypy is actively being worked on still, and in the last few months, there have been huge improvements in the speed of the tool. And there's also other exciting things being developed on top of Mypy. One that I can't wait to use is dmypy, which is a Mypy daemon that caches the state of your program and its types in memory, so it's incredibly fast to use on subsequent iterations. If we zoom out from Python and look at JavaScript, we'll see a similar trend. There's been a seismic shift in the JavaScript community over the last 2 years in terms of adding static types. First with Flow, and more recently with TypeScript, static types and type checking is the future. I'll leave you with this quote from Guido van Rossum, the creator of Python. And in this quote, even he acknowledges the power of static types. I learned a painful lesson that for small programs, dynamic typing is great. For large programs, you have to have a more disciplined approach. And it helps if the language actually gives you that discipline rather than telling you, well, you can do whatever you want. Static types and Mypy gives you this discipline in Python. Thank you.